Air pressure. You already looked at air pressure yesterday with your air pressure demos or the stations that we had set up. From that, you saw that air pressure moves in all directions. It pushes down, it pushes sideways, it pushes up. You were able to see that it moves from high to low pressure. So we're going to be looking at just air pressure in a little bit more detail. But first we need to know, what is air pressure? Well, it's simply the pressure exerted by the weight of air. Now, we don't think about air as having weight because you don't even feel the air around you. But the reason you don't feel it around you is because it is exerted in all directions. And when I say exerted in all directions, that just means that the force moves in all directions. So air is pushing down on you right now. If all you had was air pushing down on you, you would be completely crushed. But the same force of air that's pushing down is also pushing up, and it's pushing from both sides. So because the air is equally pushing all the way around you, you are not getting crushed by the air. Thank goodness. Otherwise, we'd all be like squished little bugs. Instead, we just don't even notice the air around it. We just breathe and live, and we're happy, and we just keep going on with life. But that's what air pressure is. And then the fact it's exerted in all directions is the important part of this slide, which you were able to see yesterday. So I'm going to move on. Just air pressure equals weight of air, exerted in all directions, or goes in all directions is an easy way to write that down. Okay, next slide. Measuring air pressure. So we are going to look at, because this is our meteorology unit, we're going to look at a lot of different weather instruments, and this is the first weather instrument we're going to look at. It's called a barometer. Everybody say barometer. Okay. This guy down here is the guy who invented it, Torricelli, or I don't know how to say his name. Torricelli is what I say. But look at this handsome fellow. What a nice mustache that is. Little side swoop of the hair and all that. Very handsome. But he is the one who created this barometer back in 1643. Now, you don't need to know that. Just write down the bolded stuff. But it always amazes me that people would do such good things with their lives way before we had technology. And then it makes me ask myself, what am I doing with my life? But anyway, he created this barometer. Now, the way the barometer works is he used mercury, which is actually very dangerous. You can use other things besides mercury. But if there's a high amount of pressure pushing down on the air or on that mercury, it forces the mercury to go up inside the tube. So the higher it is in the tube, the higher pressure it is because more pressure is pushing down. Versus if it's lower pressure, it's pushing down less, and therefore the little barometer level wouldn't go up as far, so it would look lower. So that's kind of how a barometer works. Now because we're going to talk about air pressure a lot more throughout this unit, but notice the first three letters of barometer is bar, B-A-R. The way that I kind of remember this is you have negative peer pressure to go to the bar, okay? So anytime you see bar in a word, you can think of pressure, because again, you have negative peer pressure to go to a bar. And I'm just really emphasizing negative, okay? And then the unit is millibars, but again, it ends in B-A-R. So as long as you are thinking bar, pressure, then you should be able to remember that. So clear the slide, and let's move right along. Grip talk. So how do you think we get different pressures on the earth? So there's all sorts of different air pressure on the earth. What causes that difference? I'll let you pause the video while you chat about this for just a moment. Okay, how we get different pressures? It is because of the unequal heating of the Earth's surface. So the Earth is not evenly heated. Okay, what part of the Earth is the warmest? That would be the equator, which hopefully you remember. So the equator gets the most direct light, so it's going to be very warm there. The poles are getting really indirect light, therefore it's going to be very cold. Well, because they are different temperatures, they therefore have different pressures. So solar radiation is the ultimate thing causing different pressures on Earth. Solar radiation is also the main source of wind energy. So it's the energy source for wind. Why are we talking about wind? Because of pressure differences? Well, that's because pressure differences are balanced out by wind. You already know air moves from high pressure to low pressure. So if you have a bunch of high pressure at the poles, it's going to want to push that air down towards the equator, going from high to low in order to even that out. In this little map up here, you have high pressure by the circle. Wind would go from high to low, so you would know the direction that the air is moving. So we have differences in pressure because of temperature differences, and because of that, we have wind, because that's how the Earth likes to balance itself out. So unequal heating of the Earth's surface causes pressure differences, aka the different temperatures around the Earth. And solar radiation is the energy source for wind. Remember, you can just use a capital E for energy. You may notice this if it's ever really hot in one room and cold in the other room, and you open the door, you can feel a big draft or just the air go whoosh right by you. That's because those two rooms had differences in pressure. And the Earth doesn't want to be unbalanced. It wants to always be balanced out. So it has to move in order to make that adjustment. Okay, moving on. Pressure differences. We connect points on a weather map using something called isobars. So again, here is that the word bar. Remember, negative peer pressure, so you're thinking it has to do with pressure. The other day you did connect the dots. You were looking at isotherms, and isotherms connect points of equal temperature. Well, but now you have isobar, and you think therm, you think temperature, bar, you think pressure. So that should help you to keep those two words alike. So this map over here is showing you different isobars. So anywhere on this circle that I'm outlining is a pressure of 1,044. Anything on this line over here is 1,005. So anywhere on the same line is going to have equal pressure. This works really well for weathermen or meteorologists because it can help them see where air masses are, and it kind of shows, or it does show, the direction wind is going. Because again, wind goes from high pressure to low pressure, so high to low. You know how the air is moving, therefore you know where air masses will move to. You know where different, or you have an idea at least of the different weather of where it's going to go and why it's doing that. You also know where the wind is going to be very strong versus very weak. Now, down here at the bottom, I know you can't really read it, but it says pressure gradient, and you don't need to write that down. But what we're going to look at next is what part of this weather map has the strongest gradient, meaning the biggest difference. And we'll look at that on our next slide. So if you aren't done, make sure you go ahead and write really, really, really fast so we can keep on going, keep this class moving. Okay, hopefully you're done. So next slide, isobars. So the closely spaced ones indicate a steep gradient or strong winds. Now, I kind of see how my bolded words don't make that sense, but if it's closely spaced, that equals high winds, you can write that down, and a steep gradient. So just write down the words that I underline. So closely spaced isobars is a steep gradient, and that means it's going to have really high winds, or you could think of them as strong winds. Widely spaced isobars is a weak gradient, and it's light winds. So again, just write down the things I'm underlining in green. So if we look down at our weather map, I'll switch to, let's see, what color do I want to pick? Purple for ECU. Okay, so if we look down at this weather map, the part over here has very closely spaced isobars. So what I would know from looking at that means it's a very steep gradient, just like when you look at a topographic map, closely spaced lines means a steep elevation. This means that there's a bunch of differences really close together. And so to fix those differences, it's going to have super strong winds. Now, some people, if you think of gradient, you may think of a hill. So if you have a really steep hill and you ride your bicycle down that hill, you're going to go really, really fast. Versus if you have a very low hill, then you're going to ride the bicycle down there very much slower. Okay, so this closely spaced ones, very steep gradients, so the winds move really, really, really fast. And then over here, you have more widely spaced ones. That's going to be the least windy area. And that's just a nice little breeze, maybe blow your hair in the wind just a little bit, but not enough to mess it up. So those are your isobars, very similar to topographic maps and contour lines. Okay, here are some characteristics of low pressure and high pressure. You will need to write all of this down, so make sure that you are copying down the chart. That's probably the easiest way to take notes on this. So all of these characteristics of low and high pressure are very important, and I'm going to refer back to them a lot, and they are very easy, specific test questions. So you need to know all of them, but the good news is I have some memory tricks to help you remember them. So let's take a look at these. As you're copying, low pressure are also called cyclones. So low pressure is also called cyclone. In this pressure center, you have rising air. So the air is going up. The winds are blowing counterclockwise, giving you severe stormy weather. And the weather symbol for it is an L. Thank goodness, that makes sense for low pressure. And it's typically red. And then let's look at high pressure, then I'll tell you my memory tricks. High pressures are called anticyclones because high and low is opposite, so the opposite of a cyclone is anticyclone. The air is sinking or moving down. These winds go clockwise, so if you just want to write down clockwise, that's all you need to write down. So the winds go clockwise, giving you fair, sunny weather. And so what we mean by fair, sunny weather is just like clear skies. There's not really any clouds in the sky. So let's look at some memory tricks to help you remember all of these wonderful characteristics of your high and low pressure. So if you have a low grade, that's a bad grade, right? Oops. So if you have a low grade, that's a bad grade. So you can think low pressure, bad weather, because severe stormy weather is bad weather. Well, the way you got that low grade or that bad grade is because you were counterproductive. You were not studying, you weren't doing stuff like that. So low grades are bad grades, and you get them because of you're counterproductive. And what you want to do is you want to raise up your low bad grade. Okay? So low pressure, bad weather, counterclockwise with rising air. You can remember that because low grades or bad grades, you get them because you're counterproductive and you want those grades to go up. So there, low pressure memorized just like that. Let's look at high pressure, and I will switch colors to, let's do orange. Okay, so high pressure, if you are feeling, let's see, high pressure has good weather. So if you have a high grade, you have a good grade. And that's really all I got for you. So a high grade is a good grade, low grade is a bad grade. And I know none of you are going to make any bad grades because none of you are counterproductive. And if you have a high grade or a good grade, then the only way that grade can go is down. But we're not going to think about that. That's not going to happen for you. You're going to keep those good grades. So that's your low pressure and your high pressure systems instead. So basically what this meteorologist is telling you is the reason you have sinking and rising air for low and high pressure. We're going to look at the high pressure air first. So that's what's going on up here. So you have jet streams that's going up way, way, way above you. So jet streams, as they sound, is where jets fly. So that you have planes flying up here. So you're not going to stand on the beach and feel a jet stream. They're way above your head. So these jet streams are coming together. And because they're coming together up here, there's a lot of pressure. And that's forcing the air to go down. So high pressure has sinking air because of that. The jet streams come together and it pushes air down. Now, the opposite is happening for low pressure. You have your winds, your jet streams that are moving away from each other. You can't have an area of nothing, so something has to move up and take its place. And so that's why you have rising air moving up, filling in that gap. Now, why is this so important? Well, what type of weather does low pressure have? Low pressure has bad weather, stormy weather. Think about a hurricane or a tornado or a thunderstorm. One thing all of those have in common, besides the fact that they're low pressure, is they all have clouds. Well, how do you get a cloud? You get a cloud because you have air that rises up, and as it increases in altitude, it cools, it condenses, and it creates a cloud. If you have sinking air, like you do in high pressure, can you get a cloud? No. You cannot get a cloud. There is no cloud, because the only way to get a cloud is if that air is rising. And you need to understand this. So I hope you're all really paying attention. If you have rising air, you now get clouds. And because you have those clouds, you're going to have bad weather, or you can have bad weather. Sinking air, like in high pressure, the reason it's good weather is because there's sinking air and there are no clouds. You don't get a cloud because of that air sinking. So that's basically what that meteorologist was explaining. If you want to go back and watch him later, all of this stuff is on Canvas. So wind, what causes wind? Well, we actually have already talked about this. Okay, wind is a result of a horizontal difference in air pressure. AKA, if you really just want to write this down, it's a difference in a result of a difference in air pressure, or just something about that. You know wind is horizontal, so why write that down? Okay, you have wind because you have differences in air pressure. And you know that air goes from high to low pressure. So to make this fast, if you just want to go from high to low, that's all you need to write. Okay, from high to low. So we have all these differences in pressure, and because we have differences in pressure, we now have the movement of air because Earth wants to balance itself out. And so it's going to move from the areas of high pressure to the areas of low pressure. And that is what is causing our wind. Okay. Now, if you're doing abbreviations, like instead of differences, you just write diff. Okay, act like you're texting this. Maybe that will help you take notes. If you pretend you're texting your notes out. That is not an excuse to get your phone. But if that makes you write faster, then do that. But going from high to low pressure. So wind is going to be named based on the direction it goes from. Remember when we did land and sea breezes, okay? A land breeze goes from the land to the sea, and a sea breeze goes from the sea to the land. So we're naming that from where it went. Not where it's going, but from where it went. So westerlies go from west to east. A sea breeze goes from the sea to the land. That's the type of thing that you're looking at when you are naming your winds. And thankfully that makes sense, so that shouldn't be too hard to remember. Sometimes scientists do weird things and it's impossible to remember. So here's our second weather tool, a wind vane. The way that we measure our wind, the direction that the wind is coming from, so you do need to know that. Wind vane measures direction. And this, you need to know what your weather instruments look like. So here you have a picture of, or a few pictures of a wind vane. And I know what these look like, or I know that they are measuring direction, because what do they all have on them? A compass. It's going to be hard for me to know the direction my wind is blowing if I don't know what the directions are, if I don't know what is north, south, east, or west. So anytime you see something that has a compass on it, you can assume that's going to be your wind vane, and that simply is telling you the direction that the wind is going. So that is measuring wind. We do have some more wind tools, but this is just what we'll look at first. Our second wind tool, so third instrument altogether, is an anemometer. Everybody say anemometer. Okay, that's typically a word people forget because they're not used to saying it, so it's not in their head. But notice an anemometer and a wind vane do look kind of similar. So again, you know the wind vane because it has a compass. Notice this one doesn't have a compass. Your anemometer is going to tell you how fast the wind is blowing, so the wind speed. You have revolving cups that capture the air, and that way it spins just as fast as the wind is going. And you can think of it kind of as like a radar gun from what a police officer would have, and it can track the speed of the wind. So they look similar, but you know it's a wind vane if it has a compass. You know it's an anemometer if there is no compass. And this cartoon picture that I have up here, that's typically the kind of picture you see on test when they show you these questions. Okay. Jet streams. So jet streams are fast-moving rivers of air high up in the atmosphere, and they travel west to east, and they move our weather. I'm going to put a big star next to that, okay, because that is something you need to know, okay? That is my big important star. They travel west to east. The way I like to think about this is if you're in an airplane and you're flying really fast through the jet streams, you go wee all the way around the world. So west to east, and it spells wee because that would be fun. So you're flying a plane and you're wee all the way around the world. I know you probably think I'm crazy, but I guarantee that will help you remember it. Okay, jet streams, they're just really fast moving rivers of air. They move our weather. So if we focus on the U.S. right here in this, if we focus on the U.S. in this diagram right up here, if you could imagine a meteorologist, they're probably going to say, like, we have some precipitation from over here and it's moving towards us this way. That's just the direction that our weather always comes. Usually our weather is coming from the upper north west, but sometimes we do get some weather from this region down here. We'll talk about that later. But our weather, so our weather moves west to east because the jet streams go west to east, and you remember that because we all go wee all the way around the world. Okay, technically there's two jet streams. We only focus on this polar one because that's what affects our personal weather, and that's what we're most concerned about. Okay, so I'm going to move on. Hopefully you're done writing. Global winds, and just hang on there with me, guys. We're almost done with these notes. Okay, global winds. We have winds that go all around the globe. And the purpose of these global winds is to create balance. Okay, I told you on Unit 1, we're going to come back to this a lot. The earth likes to be balanced. So how does it balance itself out? Well, that's what the second bullet's talking about. It moves the cold air from the poles down to the equator, and it moves the warm air from the equator up to the poles. So it's just a giant convection current. And because that's moving over the entire globe, both the northern and the southern hemisphere, that's why we call them global winds. So global winds balance out stuff around the earth, and it does that by taking cold air from the poles to the equator, warm air from the equator up to the poles. So the Coriolis effect. This is also a very important effect to learn and to know. You're probably familiar with it, but everybody say Coriolis. Coriolis. I really hope y'all repeat me when I say this stuff. Otherwise, I'm just going to feel silly. But the Coriolis effect, all that it's talking about is it causes the global winds to curve. And it also causes ocean currents to curve, which is important because we'll come back to that in another unit. But the Coriolis effect causes it to curve. So we have the earth. There's my equator. We know that the warm air from the equator wants to go up to the poles, and the cold air from the poles wants to go down to the equator. Now, in a perfect world, this would just go straight up and down. But it can't do that because the world is not perfect. So we have all of these curving things that go on. And that's what the Coriolis effect is doing. It's shifting the winds. And the reason this happens is because the earth is rotating. Okay? The Coriolis effect curves global winds because of the rotation of the earth. Now, I always have some students that say, whenever I ask, what does the Coriolis effect cause? They say, global winds. No, it doesn't. You're wrong if you say that. The Coriolis effect did not create global winds. It simply curved them or deflected them. That's all it did. And what created the Coriolis effect? So again, I've had people say, global winds. No, okay, the rotation of the earth. Because the earth is spinning so fast, those winds get deflected. Now, the winds in the northern hemisphere are deflected to the right, and the winds in the southern hemisphere are deflected to the left. And so the way I remember this is if I said, "Hey, Bob, do you live in the northern hemisphere?" Bob would say, "That's right, I do." And so because he says, "That's right," therefore the winds in the northern hemisphere go to the right. And then what's the only hemisphere left? The southern hemisphere. So therefore those winds go to the south. I mean to the left. I don't know what I'm saying. Okay, so let's look at that again. Here we have Bob. Good old Bob. Okay, so I say, "Bob, do you live in the northern hemisphere?" And again he says, "That's right." And because he's saying that's right, oh no, Bob went away. Anyway, because he's saying that's right, those winds in the northern hemisphere go to the right. And what's the only hemisphere left? The southern hemisphere. Therefore, they go to the left. Now, again, y'all probably think I'm crazy, but these memory things help you to actually remember, and there's so many little details, you got to make sure you remember it. So when you see someone, one of your classmates in the hallway, you can say, "Hey, so-and-so, do you live in the northern hemisphere?" And if they say, "That's right," then you know they learned something in earth science. So maybe y'all can test out Kiva, Thomas, Mercy, Peyton, any of those that were in my class last semester, see if they remember this. Okay, so that is the Coriolis effect. Here we have a couple of our global winds. One is trade winds. Trade winds go from the east to west. The reason they're called trade winds, though, is because they were important for, you guessed it, trade. Then you have westerlies, and westerlies are called westerlies because they go from the west to the east. Jet streams are technically a type of westerly because they also go west to east. Then you have polar easterlies. Polar easterlies are located in the poles, and they go east to west. That's why they are called easterlies. So those are our main global winds. As long as you kind of just remember how winds are named, you should be good on this one. So some of you may be looking at this diagram down here, and you're like, "But Miss Collins, I thought you just said everything in the northern hemisphere is deflected to the right with global winds." And in this picture, it looks like some of them are going left, some of them are going right. Well, there's a reason for this, and that's because, think about it, if you're standing at the front of the room and you look to the back of the room, your right is going to be different than someone who's facing you. If they pointed right, they point the opposite direction. When we curve these winds to the right or the left, it depends where they're coming from. So these winds right here, they are going up, and so when they curve right, that's this way. Because these are starting from the other way, you can think of them facing the opposite direction, and they curve that other way. Now, if what I just said just confused you, ignore me, okay? Just know that Coriolis effect, the winds go to the right in the northern hemisphere, left in the southern hemisphere. If this confused you and you just can't let it go and you must understand it, then on the previous slide, there was a video that explained, my next slide, there's a video that explains it, and you're welcome to watch it. But I will not ask you any questions on the test about that in particular. So those are the global winds, and that is the last slide of notes for this section of this unit.